The next thing we want to talk about here is conditional probability. What does it mean for something to be conditional? So when somebody said, like, what's a scenario where somebody uses the word conditional, like, well, what does that mean? Okay, so something has to have happened, right? So like first period said they're talking about conditional love. What's that mean? Okay, so to love you, there has to be something that, like you've got your parents love you because somebody pays them to. That's the condition. No, okay. So they have unconditional love for you, right? Okay. So conditional means that there's some requirement that has been made already, right? Or that has to be made, right? When we talk about conditional probability, something has to have happened already. Okay. It says here that the conditional probability is the probability of an event A given that event B has already occurred. So the condition is that event B has already occurred. Does that make sense? Okay. So some scenarios that we might see is if I ask you to tell me what's the probability that you pick an ace out of a deck of cards given or provided that you have already picked and kept an ace out. Does that make sense? So do you see how the probability would change on that second selection because of what has already happened? Does that make sense? So usually conditional probability, when we talk about it, we're talking about reduced sample spaces. And we might even be talking about reduced outcomes that align with the event in the probability. So for instance, if I say what is the probability of, let's see here, what's the probability of choosing an ace No, I don't make those decisions. So if I ask what's the probability that we pick an ace on the second draw, and this line here means given or given that you picked an ace, and I'm going to say that we kept it on the first draw. Okay, think about what that would mean. How many aces are there on the first draw? 4, right? Out of how many cards? 52, okay? I've already pulled one of those 4, and I put it in my pocket, okay? So now, have I changed the sample space? On the second draw, I'm only picking out of 51, right? Have I changed the outcomes that align with the event that we're talking about? Yes, I've changed the number of outcomes from 4 aces now to 3 aces. So, the probability of this happening would be 3 out of 51. Does that make sense? Okay. So conditional probabilities mess with our sample spaces. Okay. And a lot of times dealing with conditional probabilities, we like to structure our data, our information in tables or diagrams or charts, and we'll talk about some of those things today. But we also, in certain times when we don't necessarily have all of the raw data, but we just have the processed raw data, meaning that we have maybe just the percentages, just the individual probabilities, then formulas are going to be necessary. All right. So since we were asking a question about probability given an already known condition, we need to divide out the probability of the given event, okay? And I'll give that'll make maybe a little bit more sense when I give you an example here of a specific situation. But the general formula for conditional probability, you're going to see this written 2 different ways. I don't like the way our textbook writes it, but this is the way it writes it. It says the probability of A, and that line right there stands for the phrase given that. Okay. When we were in, those of you that took college algebra, and you maybe even saw us a little bit in algebra 2, you did set notation, set theory, and we did work with intervals and something called set builder notation. Like if I said like x is greater than 5, the actual formal way we should write that solution is that we write a curly brace and we write a variable that we're talking about, and we write this, and then we say greater than or equal to 5, and we close it off. That's the formal way of writing the solution for x is greater than or equal to 5. And the way we read that is it's x such that. That vertical bar in that situation stands for such that. In probability, it stands for given that. Okay? Not a huge deal. That vertical bar in some aspects of mathematics in some branches talks about division, talks about factors, okay, or is divisible by. But in this case, like I said, it stands for given that. And what we have here is the idea, so the formula says, and we'll discuss the creation of this formula later on, but it's the probability of A and B, then divided by the probability of B. Okay? A lot of formulas in other textbooks that talk about general formula for conditional probability, they will write it this way. Because if I'm talking about A and B being events, which one of those would you get used to happening first? You would think A happened first, right? So what they'll ask you, or what they'll write, is they'll say, okay, what's the probability of event B given that event A has already happened, because event A, alphabetically, would have been first. Does that make sense? So they do it that way. And then they still have probability of A and B up top, but now what would be on the bottom? What was in the bottom here? So that thing in the back is always the object that's on the bottom. Okay. Later on, we'll see there's a story problem. I'm not sure what section it is, maybe 3.3. It talks about picking out like white, like poker chips and black poker chips, and what's the probability of picking a black one given I've already picked a white one or something like that. So it'll say probability B given that W. Okay. So then we say, oh, what's the probability that it's black and white, then divided by probability of what? W. Okay? So we got to understand that structure, that the top is always the two events with and stuck between them. Okay? So the two events happening at the same time, or successively. We'll talk about dependence and independence here in a little bit. And then it's always divided by then the condition. Okay? Given A has already occurred, A is a condition, or W in this case would be the condition. Is that okay with everybody? Now you might, because we talked about this yesterday, you might not see it written with the word and. They might use the math notation with that intersection symbol. So you might see P of A given B is equal to P A intersect B divided by P of B. And just that notation kind of sometimes scares people. So I want to make sure we talk about that, and don't let it scare you. You okay with that? All right, so let's talk about an example. We've already talked about this example, right? So let's use that as our situation. Now, so what this means is I want to know what is the probability that I pick an ace and an ace when we are pulling cards out of this deck. So I'm going to put ace 1, and it doesn't matter the order that you do these. Ace on the first pull and ace on the second pull is the way I'm going to write it. Just chronologically, I think that makes sense. And then down here on the bottom, I'm going to divide out probability of ace on the first pull. So the subscripts tell me what draw, what the order of my drawings are. So if I pick an ace out, okay, and I keep it, pick an ace out and I keep it, does that impact my second withdrawal, my second choice? Yeah, okay, so that's called, we're doing without replacement is what this is called, okay, probability without replacement. So the probability of two events that are dependent, okay, and we've got the and here. We actually multiply, and we'll talk about the multiplication rules and why this is the case in the next section, but we multiply their individual probabilities. Okay, so probability of picking an ace on the first draw is 4 out of 52. Does that make sense? Okay. I keep that ace, put it in my pocket, and now what's the probability that I pick an ace on the second draw? 3 out of 51. Okay, so we're going to, because they're independent, they're dependent events and they're and, we're going, this is the multiplication rule, so we multiply. Then, the bottom is the probability that on the first draw we picked an ace. Well, that was 4 out of 52, right? Do those cancel out? And leave you 3 out of 51? Okay. And now that might be almost a trivial question or trivial probability because we could kind of visualize that in our minds with knowing what the deck looks like and knowing what that situation. He said we took a card out that was an ace out of the first draw, put that in our pocket. Now, we understood that that changed the sample space and it changed the outcomes or the outcomes that align with the event. So we know we should only have 3 outcomes and we should only have 51 things to choose from. So that 3 out of 51 is something that we already inherently knew, right? But do you see how the formula verifies that? Okay. So there's going to be questions eventually where we can't really visualize the sample space very well. Okay. So let me jump real quick. You don't have to write this down because you'll have these eventually. Let's see here. So the probability that Sam parks in a no parking zone and gets a parking ticket is 6%. And the probability that Sam cannot find a legal parking space and has to park in the no parking zone is 20%. On Tuesday, Sam arrives at school and has to park in a no parking zone. Find the probability that he will get a parking ticket. Okay? So that's kind of messy, and it doesn't use the word given that in there. That's usually the kind of identifying statement or phrase in a story problem that tells us, oh, it's conditional probability, okay? But if we read the scenario, it says he arrives at school and has to park in a no parking zone. So he's parking in a no parking zone and wants to know, what's the probability he gets a ticket? So does it make sense that we're asking probability gets a ticket given we know where he's parking, right? He is parking in a no park zone. Does that make sense to everybody? Okay. Now, thinking about the probabilities that I just gave you, do we have a good visual of the sample space like we do with the cards? No. Okay. So, in this situation, we have to rely on the formula that says probability of getting a ticket and no parking zone, which I think is a probability they give us up here. And then we would divide that by parking in a no park zone. So we grab those two probabilities, divide them out, and we'll have then the likelihood of him getting a ticket that day. Does that make sense? Okay. And we'll get into more detail with that when we get into that section, but that's what conditional probability is that something has to be met first. Okay, and that then narrows our focus on likely events and sample spaces. Okay, here's an example. Now, I don't know yet. We'll see in section 3.3. The way I've got this set up is fine. It works, but it's hard to explain the logic and the separation of these values in the Venn diagram. So I'm going to ask you to just kind of wipe those values out, just cross them. I will change them here in a minute. They're fine. They work, but I think it's kind of cluttered and messy the way that we have to think about it if we write them that way. So in a Group of 100 sports car buyers. 40 bought alarm systems, 30 purchased bucket seats, and 20 purchased an alarm system and bucket seats. If a car buyer chosen at random bought an alarm system, what is the probability they also bought bucket seats? Okay. Now, before we get into this problem, because this happened first period, we get like halfway through, somebody raises their hand. What's a bucket seat? Do we know what bucket seats are? So most of them do. They're like your driver's seat. Okay, so you ever been in like an SUV or a van, and that middle row is 2 individual seats? Those are bucket seats. Sometimes they're called like captain chairs or captain seats or whatever. Usually, like a bucket seat is a little bit more of a contour to sit in, kind of like more you guys see like racing seats. You ever seen those before? Okay, so those are bucket seats, but they're just not a bench. Like in an F-150, the middle console raises up and you can put somebody in the middle. Okay, that's a bench seat, right? So bucket seats are individual seats. Okay, that's all we're talking about here. Yeah. All right. So it says, what is the probability knowing that it says if a buyer chosen at random bought an alarm system, what is the probability that they also bought bucket seats? So what do you know that they already bought? If you read this phrase, you know they bought an alarm system. So there's the condition. Does that make sense? Okay. So the question is, what's the probability that they bought bucket seats given they have an alarm system? Okay. So using this information then, we talk about our formula, probability of bucket seats and an alarm, divided then by the probability that they had an alarm. Okay? So let's kind of walk through this analytically with the formula, and then we'll see how a Venn diagram can maybe come into play. So bucket seats and an alarm. Okay, how many bought bucket seats and alarms? 20, right? Okay, 20 out of 100, or 0.2, right? How many buyers bought an alarm system? 40 out of 100, or 0.4. Okay, so now bucket seats given they had an alarm system, that is the probability of buckets and an alarm divided in by probability of an alarm, right? Do we have that numerator somewhere? That's the first one, 0.2, right? Do we have the bottom one? 0.4. What's that divide out to? What's 2 divided by 4? 1/2. All right, so 0.5, okay, because of the same place value, we can just ignore the decimal, just 2 divided by 4. Okay, so if you know the condition, so if I ask what's the probability you buy bucket seats, okay, that is going to be a lower probability than what this is, because I've narrowed the focus. I'm now saying, look at the people that have already bought an alarm system. What's the probability that they also have a bucket or bucket seats? Okay, so 0.5 is that probability. Okay, let's look at the situation down here with a Venn diagram. And to be honest, I'm just going to create a little bit extra room. I'm going to come over and do the Venn diagram here. All right, so Venn diagrams, you got 2 situations. You got alarms, okay, and you've got bucket seats. Okay, now when we have an alarm and we have bucket seats, they overlap, right? The overlap here, when we do a Venn diagram, is what is shared, correct? Which ones are shared? How many should go in there of the people that are in my story here? 20 purchased an alarm system and bucket seats, right? So 20 should go in there. Now, how many, if we're looking at that system or story, how many bought alarms? 40. Would you guys agree that I've already got 20 in here of that 40? Does that make sense? Okay. So, and that's kind of where my picture that I had drawn at the beginning gets a little bit confusing. So I'm just going to put 20 there. So 20 alarm, separate. Only these 20 have just an alarm. These 20 have an alarm, but they also have bucket seats, right? Okay. Now over here in this bubble, how many bought bucket seats? Okay, so just 10 just bought buckets and no alarm, right? Okay. So how many is that? 50. So of all the people that bought sports cars, there's 50 that didn't buy an alarm and didn't buy bucket seats. Does that make sense? So there's maybe another configuration that those 50 purchased. So now the question is, given that they bought an alarm, okay? Given that they bought an alarm, so if I'm talking about given they bought an alarm, I'm looking right there, right? That's the group I'm looking at. How many people are in there? Okay, 40. And how many did buckets and an alarm? 20, right? So do you see 20 being buckets and alarm, be this numerator, and probability that they had an alarm is just looking at that bubble of 40. Is that still 0.5? Okay, so do you see what conditional probability does? Conditional probability, visually, hopefully there, instead of looking at that entire rectangle, now we just focus, because I have that condition that they bought an alarm, I'm just now focusing on that blue bubble and the information in there. Does that make sense? Okay, what's confusing? Think about verbalizing that better and we can, talk about what's confusing. Okay. The 20 went. Oh, these 20? And that I get that. So you could maybe argue that. Yes, I guess I can see where you can argue that. Those are so obviously when an author writes a problem, they've got kind of their internal understanding of what they mean by that prose style writing. This is what they wanted, but I can see, and you could be right, thinking of it your way. And those are things that we can maybe negotiate or talk about if they occur. When I write the questions, I will make sure that that is minimized. Yes. 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 I agree. Don't get caught up too much. Don't get caught up too much on the problem. Does the conception or the conceptual idea of conditional probability, where because now you have a given requirement that had to be met, do you see how it reduces your focus on a probability? Okay, that's the main thing here that I want to talk about in this terminology section, and then when we get to, like I said, section 3.3, 3.2, we'll investigate the structure of the story problems and that kind of stuff a little bit more. You're good? Okay. All right. Good. Good. All right. Venn diagrams, obviously, they have their place. They have their use. And their purpose, again, is for you to visualize. If we didn't have these tools to visualize probabilities, they would be more difficult. I think some people think probability is an abstract concept. Okay. And if we're just thinking of just the raw numbers that attach to probabilities and try to decide, what do I do with these? Do I divide them? Do I multiply them? Do I multiply them, then divide them? Do I add them? It gets messy. But if you can structure things in tables or Venn diagrams, it might alleviate a little bit of that confusion, and that's the purpose of them. So Venn diagrams, like I said, you see down here, section 3.5 is an entire section devoted to them. Okay. This next example here is what we call a contingency table. Okay, and we'll actually do two that are like this, but this is section 3.4 information eventually. All it says is that we've got males and females. We've broken our sample or population into those categories, and then broken against the categories of have pets, do not have pets. Okay, so we got several variables here, whether you have a pet and your gender. Okay, says what is the probability a randomly selected person is male given that they own a pet? So what we're doing here is probability that they are male given they own a pet. Okay, and as we're doing this, I don't care if how you're going to like label your probabilities. If you want to be very specific, one thing that I always struggled with when I was first learning this stuff in high school was the abstractness of using just capital letters instead of the entire word. Okay, and a lot of times the way I learned it is that they would say, being a male, they say let that be event A, and then say having a pet, they say let that be event B, and then it asks you, well, what's the probability of A given B, and what's the probability of B given A, and it was so hard that you had to go back through like 2 or 3 lines of connections to determine, well, what did A given B really mean? So if you can use phrases or statements to help you remember what actually you're being asked here, that might, again, alleviate some issues. So if this is a given condition, okay, knowing that I have to have a pet, what is the probability of being male? So now my hope is that you see with this contingency table, all we're doing now is focusing on that column right there. Okay, I'm no longer dealing with 100% of the population. Does that make sense? Okay, because I'm telling you have to have a pet, so only 86% have a pet. So then I have to determine, well, what is the probability of being male then out of that 86% of the population? So working through this, we have probability that they are male and have a pet. That's my numerator. And what's the denominator going to be? Yep. Have a pet. So what's the probability that they're male and have a pet? 41%, right? That's the intersection of those two, that row and that column. So that's the numerator. And now what's the probability that somebody has a pet? 86%. So we'll divide that out. 0.41 divided by 0.86. And we get 0.477-ish. Okay. But the whole idea here is hopefully you can see with the visual that the conditional probability idea no longer is worried about us out of 100. Okay. When we get the condition, it narrows our sample space, narrows our outcomes that are aligned with our events. Well, that's and I get that because but when it asks us to focus on the condition that we know they had an alarm, that automatically makes my denominator then 40. I don't want to spend more time on this. We'll come back to this question here later on in another section. We'll revisit this, and because we should be able to take this scenario here and develop it into a contingency table. Okay. I prefer to look at contingency tables than Venn diagrams. I think these tables make more sense to me. The intersection of rows and columns, just visually to me, makes more sense than the intersection of the bubbles. Let's go. There's one more down here at the bottom, and then we'll come back up if we have time to do those other ones. It says the table describes the distribution of a random sample of 100 people organized by gender and handedness. Okay, so with contingency tables, and they don't always fill these things in, but it makes sense to have total columns and total rows. Okay, so if I look at the right-handed people and add straight down, how many right-handed people are there? 87. How many left-handed? 13. If I go totals, how many males are there? 52. How many females? 48. Okay. So now, how many? So if I have 52 males, 48 females, that's 100 people. If I have 87 right-handed people and 13 left-handed people, does that still add up to 100? So your contingency tables, your totals, should all merge back over to this last little cell here. And that bottom row and that total column should all equate to the same quantity. Say it again. Yes, yes. But it doesn't, it won't always tell you 100. They might just give you this here without the scenario. So now, what's the probability of being a male? 52%, right? And I'm just going to write it as 0.52. So everything's going to be out of 100, so 0.52. What's the probability of being a female? 0.48. What's the probability of being right-handed? 0.87. What's the probability of being left-handed? 0.13. Are those okay? Are we pretty good at those? Okay. Now, probability of being male and right-handed. So now it's the intersection of the male row and the right-handed column. So 0.43. Okay. Probability of being female and left-handed. 0.04. It's just that one now, right? It's the intersection of the female row and the left-handed column. So 0.04. All right, now, what's the this one might be a little tricky. What's the probability of being male or female? Okay, 100%. I guess it's the next one that's a little bit trickier. What's the probability of being male or right-handed? So we talked yesterday, when we see or, what operation does that refer to? Adding. So I'm going to look at the individuals, probability of being male plus probability of being right-handed. So what's probability of being a male? 0.87. What's probability? Oh, sorry. Male was 0.52, right? And so 0.52. And being right-handed was 0.87, right? What do you get if you add those together? Something bigger than 1, and that is a problem and probability, right? Okay, we can't have something more than 100%. Okay, so what has happened here? In this, when I said probability of being a male, did those 43 people get added in as being male? So those 43 got added in right there as being male. Did they also get added in as being right-handed? So those 43 people, are they the same 43 people each time? So they got counted twice, right? So I only want to count them how many times in the probability? Once. So we got to remove that 0.43. And now if we do that, we will get this probability. So what that means to us is that we need to remove the probability of being male and right-handed at the same time. So those are events that are, we said we used the word mutually exclusive yesterday. Okay? If I flip a coin, those two events, heads and tails, cannot happen at the same time, right? So they are mutually exclusive. These events are not mutually exclusive, which means they can happen at the same time. So when they can happen at the same time, through the addition formula, we add them in twice, and we got to take care of that. Okay. What about too much erasing. What about let's skip down. So this one would be the same thing, but they're just being female and left-handed. What's the probability of being M prime. What's the complement of being a male? Female. So it's 0.48, right? Okay. So let's do it right-handed given that they are a male. So probability of right-handed given they're a male. So that would be probability of right-handed and male divided by probability of male, right? So right-handed and a male. Right-handed and a male. That'd be those people there, right? 0.43. And now probability of being a male, 0.52. Okay, let's divide that out. 0.43 divided by 0.52 gives us 0.826. Okay, now here's my question. Can we look at this table a little bit differently than using the formula and say, okay, probability of being right-handed given that I'm a male? Are we now just looking at that right there? I know I'm a male, right? Okay. Or I know that this individual is a male, so focus just on that. Now, what's the probability then of them being right-handed? 43 divided by 52. Is that the same thing that we got right there? Okay, so the formula will do it. The formula will do the job, but the contingency table allows you maybe to maybe do it an alternative way. Some people prefer the formula. Okay, some people prefer the contingency table. I think it's a good idea to be able to learn both. Okay, because there will be situations where only the formula is going to be available to us. That question, whether that person was parking tickets and stuff like that, I don't think you can create a contingency table maybe for that. Okay, or if you can, it might be cumbersome. It might be time consuming to do that. Does this kind of make sense? Okay. Now, if you're wigged out, worried about, I didn't understand much of this, relax, you'll be fine. What we're going to do on Monday, we are going to dig into just one rule. Okay, we'll talk about I think it's the multiplication rule, and we'll see example after example after example. We'll try to get that learned and understood the best we can. And once we have that down, we'll go to the next rule of addition, which is using the word or. And we'll keep doing that until we run through all of our formulas. And then if we were to come back to 3-1, you guys would be able to breeze through this stuff. Okay? But what I'm trying to do is get these concepts understood about what does it mean to be conditional, what's it mean to maybe be independent, dependent. Oh, you had that with you. Oh, I want to carry it. It's actually a better look for you. All right, guys, so your homework